In the vast, silent theater of the cosmos, where stars are born and galaxies collide, there are wonders that defy our everyday comprehension, phenomena so grand they challenge the very limits of our imagination. We look up at the night sky and feel peace. A sense of tranquility washes over us as we gaze upon the celestial tapestry. But the universe is not always peaceful. Beneath the serene facade lies a realm of unimaginable power and cataclysmic events. It is a place of extremes, a constant dance between creation and destruction, order and chaos, unimaginable violence, cosmic collisions that dwarf anything we can conceive, and breathtaking beauty, nebulae painted across the void like celestial masterpieces. Among its most powerful denizens, lurking in the shadows of galaxies, is Sgr 618, a name whispered in astronomical circles, or TON 618. A designation that hides a truly monstrous reality. Don't let the technical name fool you, it's merely a label assigned by us. TON 618 is a true cosmic monster, a behemoth that dwarfs even the largest stars. It's not a star, burning brightly with nuclear fusion, or a galaxy, a swirling island of billions of stars, but an ultramassive black hole, a point of infinite density from which nothing, not even light, can escape. It is one of the largest ever discovered. A titan among titans in the cosmic landscape. Located over 18 billion light-years away, its light has traveled for eons to reach our telescopes. It's a relic from the early universe, a glimpse into the cosmos as it was in its infancy. Observing TON 618 is like peering back in time, witnessing the universe as it was when galaxies were still forming, to the dawn of existence, when the first stars ignited, and the cosmos began its long journey to the present day. Its gravity is so immense, so overwhelmingly powerful, it holds an entire galaxy in its grip, dictating the orbits of billions of stars. How could something so enormous form so early? What processes allowed it to grow to such an incredible size in the nascent universe? TON 618 is a profound mystery, a cosmic enigma that challenges our understanding. It challenges our understanding of cosmic evolution, forcing us to reconsider our models of how black holes and galaxies form, and the limits of our knowledge, pushing the boundaries of what we think is possible in the universe. To grasp its significance, to truly appreciate the scale of this cosmic behemoth, we must first understand black holes, the fundamental forces that shape galaxies and the blazing hearts of quasars, the most luminous objects in the universe. So let's step into the darkness, venture into the cosmic void, towards the brilliant light of a quasar powered by a monster, a journey to the edge of our understanding. In the vast expanse of the cosmos, there exist enigmatic entities that defy our everyday understanding of physics. What is a black hole? It's a region in space-time where gravity reigns supreme, so intensely strong that nothing, not even light, the fastest entity in the universe, can escape its grasp once it crosses a certain boundary. Imagine a point of no return, a cosmic vacuum cleaner from which there is no escape. These cosmic behemoths often arise from the dramatic demise of massive stars. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity, crushing itself into an infinitely small point, a singularity, the heart of a black hole. This singularity is surrounded by an event horizon, the point of no return, the boundary beyond which nothing can escape the black hole's pull. From the outside, a black hole appears as a perfect sphere of blackness, a void in the fabric of space-time. Its immense gravity warps the very fabric of space and time around it, creating bizarre distortions and gravitational lensing effects. But not all black holes are silent and dark. Take TON 618, for example. It is not silent or dark, it's not just bright, it's one of the brightest, most luminous objects in the entire observable universe. How can something associated with darkness and inescapable gravity be so incredibly bright? How? The answer lies in the chaotic dance of matter as it falls into the black hole's gravitational embrace. TON 618 is a quasar, a specific type of active galactic nucleus, or AGN, powered by a supermassive black hole residing at the center of a distant galaxy. This black hole is constantly devouring gas, cosmic dust, and even entire stars that stray too close. As this material spirals inward towards the event horizon, it forms a swirling disk of superheated matter known as an accretion disk. Friction and compression within this disk heat the material to millions of degrees Celsius. The disk glows with unimaginable intensity across the electromagnetic spectrum, from radio waves to X-rays and beyond. This intense radiation outshines the combined light of all the stars in its host galaxy. When we observe quasars like TUN 618, we are essentially seeing the light emitted from this accretion disk, not the black hole itself, which remains hidden behind the event horizon. Quasars like TUN 618 serve as cosmic lighthouses, powerful beacons illuminating the distant universe and offering us a glimpse into the violent processes of creation and destruction occurring at the hearts of galaxies. They are powered by the most extreme gravity wells in the universe, supermassive black holes consuming matter at an astonishing rate. To grasp TUN 618's size, consider this. Its black hole is about 66 billion times the mass of our Sun. For comparison, the Milky Way's central black hole, Sagittarius A*, is just over 4 million solar masses. TUN 618 is more than 15,000 times more massive. Imagine combining every star in the Milky Way. Their total mass would only match TUN 618. This is a concentration of matter that defies comparison. Its gravity dominates its entire galaxy, dictating the motion of stars and gas clouds. TUN 618 is an ultramassive black hole, a true singularity in every sense. Its scale is not just a number, it shapes its environment on a galactic level. Stars orbit at incredible speeds, bound by its inescapable pull. It is a gravitational king, ruling a vast cosmic kingdom. The sheer mass of TUN 618 is a testament to the universe's extremes. The event horizon of TUN 618 is colossal, a boundary so immense it defies easy comprehension. It represents the point of no return, where nothing, not even light, can escape the black hole's relentless pull. It spans about 1,300 astronomical units in radius, a truly staggering distance. To put that into perspective, consider the vastness of our own solar system. That's 1,300 times the distance from Earth to the Sun. Each astronomical unit is a journey of approximately 150 million kilometers, and TUN 618's event horizon stretches across 1,300 of those. If TUN 618 replaced our Sun, imagine the consequences. Every planet, including distant Neptune, which orbits at the very edge of our solar system, would be deep inside its event horizon, forever lost to its gravitational grasp. Even the Kuiper Belt, a region of icy bodies beyond Neptune and Voyager 1, humanity's farthest traveling spacecraft, would be swallowed whole, disappearing into the abyss. The event horizon would stretch far beyond anything in our solar system, encompassing a volume of space almost incomprehensible in its scale. Imagine our entire solar system, from the Sun to the outermost reaches of the Oort cloud, fitting inside this black hole. And not just once, but more than 40 times over. The sheer magnitude of this comparison highlights the extraordinary nature of TUN 618. From a distance, we'd see a perfect circle of blackness, a void in the fabric of space-time. Its edge defined by warped starlight, bent and distorted by the immense gravity. This is gravitational lensing, a beautiful, terrifying phenomenon that reveals the hidden power of these cosmic giants. TUN 618 would appear as a hole in reality, a distortion of space and time itself, utterly dwarfing our planetary system, making it seem insignificant in comparison. Its shadow would be immense, a void against the stars, a constant reminder of the immense forces at play in the universe. The scale of its consumption is mind-boggling, as it devours matter equivalent to entire stars. This is the true presence of TUN 618, a cosmic behemoth, a region of inescapable gravity that could swallow solar systems whole, leaving nothing behind. It's a cosmic abyss beyond imagination, a testament to the extreme phenomena that exist in the vastness of space. TUN 618's discovery began with a search for faint blue stars at the Tonantzintla Observatory in Mexico in the 1950s. It was catalogued as a faint blue star-like object, just another point of light. But radio astronomy revealed something unusual. Some of these blue stars were powerful radio sources. These became known as quasars. In 1970, astronomers obtained a spectrum of TUN 618's light. The The spectrum was bizarre. Emission lines were broad and massively redshifted. This indicated it was billions of light years away, moving at tremendous speed. The broad line showed gas swirling around a central object at thousands of kilometers per second. Only an object with immense gravity could cause such speeds. The pieces fit. Ton 618 was not a star, but a quasar powered by a supermassive black hole. That faint blue dot turned out to be one of the most luminous and massive objects ever seen, a cosmic titan hiding in plain sight. How do we weigh an invisible object billions of light years away? The answer lies in the light from the swirling gas around the black hole. The Doppler effect broadens the spectral lines. Faster gas means broader lines. By measuring this broadening, astronomers calculate the gas's velocity. Combine that with the distance from the black hole, estimated from the quasar's brightness, and you get the mass. The result for Ton 618, 66 billion solar masses. It's a triumph of scientific detective work. Ton 618's mass isn't just impressive, it's a challenge to our understanding of the universe. We see it as it was in the early universe, only a few billion years after the Big Bang. Standard models say black holes grow slowly, but Ton 618 reached 66 billion solar masses incredibly fast. Did it start as a much larger seed, or did it grow by breaking the rules we know? Ton 618 forces us to rethink how black holes form and grow. Ton 618 is more than a puzzle, it's a probe of the early universe. Its brilliant light travels across billions of light years, passing through ancient hydrogen clouds. These clouds leave fingerprints, absorption lines in the quasar's spectrum, creating a Lyman alpha forest. By studying these lines, astronomers map the structure of the young universe. Ton 618 illuminates the cosmic web, revealing how galaxies began to form. It's a beacon shining backward into the dawn of time. Ton 618 is a marvel of physics, a symbol of humility and a driver of discovery. It reminds us of our smallness. Our solar system could vanish inside it without a trace. Yet its existence inspires wonder and curiosity. Found by accident, it challenges our theories and pushes science forward. For every answer, it raises new questions. How did it grow so large? Are there even bigger black holes? Ton 618 embodies the spirit of exploration. The next time you look at the night sky, remember this impossible giant shining from the dawn of time. The journey to understand our universe has only just begun. For as long as we've gazed at the night sky since the dawn of our awareness, we've wondered about our place in the universe, pondering the vastness and our connection to it all. The cosmos has always beckoned us, a silent invitation to explore the unknown. Black holes, once just wild predictions from Einstein's theories, existing only in the realm of complex equations and thought experiments, were long considered invisible, their nature shrouded in mystery, their existence inferred only by their effects on nearby stars, a subtle dance of gravity hinting at something unseen. We could only imagine the true form of these cosmic behemoths. But in April 2019, everything changed. A new chapter in our understanding of the universe was about to be written. For the first time, after years of tireless work, humanity captured an image, a direct visual confirmation of a supermassive black hole, a cosmic giant lurking at the heart of galaxy Messier 87, a distant island universe. This wasn't just another telescope photo, another pretty picture of a nebula or a distant star. It was a scientific milestone, a monumental achievement that redefined our perception of reality, confirming one of general relativity's boldest predictions, validating Einstein's genius once again. The image, a symbol of human ingenuity, a glowing ring of superheated gas swirling around the abyss, encircling a perfect sphere of darkness, the point of no return, the black hole's shadow, the event horizon itself. Suddenly, black holes were no longer just theoretical, abstract concepts confined to textbooks. They were real, observable, and within our reach. The universe had revealed one of its deepest secrets. This achievement was the result of decades of dreaming, of countless hours of research and dedication, and a global collaboration on a scale never seen before. Scientists from around the world united in a common goal. It required connecting observatories across continents, creating a virtual telescope the size of the Earth, and processing mountains of data, sifting through petabytes of information to extract the faintest signal. The result is more than data, more than just numbers and statistics. It's a cosmic portrait painted by the universe and captured by human hands, a masterpiece of science and collaboration. This image bridges 55 million light-years, a journey across unimaginable distances, letting us peer into the heart of a distant galaxy, witnessing the power and mystery of a black hole firsthand. It's a testament to human curiosity, to our insatiable desire to understand the cosmos, and what we can achieve together when we unite our minds and resources for a common purpose. The universe is filled with wonders, waiting to be discovered, and we've only just begun to see them. This is just the beginning of our exploration of the cosmos. The journey of discovery continues, beckoning us towards new horizons and deeper understanding. So what is a black hole? Imagine matter so densely packed that its gravity traps even light. Black holes are born from collapsing stars, but M87 is in a different league, a supermassive black hole. These giants, millions or billions of times more massive than our Sun, anchor entire galaxies, including our own. They grow over billions of years, devouring stars, gas, and even other black holes. Their immense gravity shapes galaxies and fuels brilliant cosmic phenomena like quasars. Supermassive black holes are not just curiosities, they're fundamental to the structure and evolution of the universe. By studying them, we're piecing together the story of how galaxies form and evolve. M87 is a key to understanding cosmic history. These objects are the engines of galactic evolution. Unlocking their secrets helps us understand the universe itself. To truly grasp the profound significance of the M87 image, we need to step back and consider the sheer scale of what we're looking at. It's not just a picture, it's a portal to understanding the universe's most extreme phenomena. We need to talk scale. We're talking about distances and masses that are almost impossible to comprehend on a human level. M87 is 55 million light-years away, a distance so vast that it challenges our everyday understanding of space. The light we captured to create this image began its journey across the cosmos before humans even existed on Earth. It's a snapshot from deep time. It contains the mass of 6.5 billion suns, a concentration of matter so immense that it warps the very fabric of space-time around it. It's the gravitational anchor holding together a galaxy of over 1 trillion stars, each a sun in its own right, swirling around this central behemoth. Now imagine if we were to place this black hole in our own solar system. Its event horizon, the point of no return, would engulf everything out to Pluto and even beyond, swallowing all the planets in its wake. Observing it from Earth at such an incredible distance is like trying to spot a donut sitting on the surface of the moon, a feat that seems almost impossible, pushing the limits of what our technology can achieve. Yet its immense size, its sheer gravitational power, made it just large enough for us to glimpse it with our most advanced technology, a network of telescopes spread across the globe. Messier 87, its host galaxy, is not just any galaxy. It's a giant among galaxies, a dominant force in its cosmic neighborhood, influencing the evolution of countless other galaxies around it. By studying M87 and its relationship with its host galaxy, we can learn invaluable lessons about the life cycles of massive galaxies, their formation, and their evolution over billions of years. The story of this black hole is inextricably linked to the story of its colossal host galaxy. They are two pieces of the same puzzle, each influencing the other in profound ways. It's more than just an image, it's a window into the most extreme environments and phenomena in the universe, pushing the boundaries of our understanding of physics and astronomy. How do you photograph something so distant and small? You build a virtual telescope the size of Earth. The Event Horizon Telescope, EHT, is a global network of radio telescopes synchronized with atomic clocks, all aimed at M87 Using very long baseline interferometry, the EHT combined data from observatories across continents, simulating a planet-sized dish. The challenge was immense, coordinating observations, perfect weather, and transporting petabytes of data on hard drives. Hundreds of scientists collaborated, developing new algorithms to reconstruct the image from incomplete data. 4 independent teams analyzed the data, all revealing the same result: a glowing ring around a dark void. The EHT's success was a triumph of technology and teamwork. It proved that with ingenuity, we can overcome even the greatest observational challenges. The virtual telescope worked. We had our first direct look at a black hole's shadow. The groundbreaking EHT image, a monumental achievement in astrophysics, doesn't show the black hole itself directly. What we're seeing isn't the black hole's surface because, well, it doesn't have one in the traditional sense. Instead, it reveals its shadow, a dark silhouette cast against the intensely glowing accretion disk surrounding it. This shadow is our window into understanding these enigmatic objects. The accretion disk is a swirling, spinning ring of superheated gas and dust, a cosmic maelstrom of matter pulled inexorably towards the black hole's center. As this material spirals inward, it's compressed and heated to unimaginable temperatures, emitting powerful radio waves that our telescopes can detect across vast cosmic distances. At the very heart of this chaotic dance lies the event horizon, the ultimate point of no return, the boundary beyond which nothing, not even light, can escape the black hole's relentless grip. It's a region where gravity reigns supreme, an inescapable abyss, where the laws of physics as we know them begin to break down. Interestingly, the shadow we observe appears significantly larger than the actual event horizon itself. This is because the black hole's immense gravity warps and bends the light rays traveling around it, a phenomenon known as gravitational lensing. This remarkable effect, predicted over a century ago by Einstein's theory of general relativity, showcases the profound influence of gravity on the fabric of space-time. The bending of light amplifies the apparent size of the shadow, creating the distinctive fiery ring that we observe in the image. Therefore, the shadow's size and shape provide a crucial and direct test of general relativity in one of the most extreme environments imaginable. Precise measurements of the shadow have not only confirmed Einstein's theory, but have done so with unprecedented accuracy, solidifying its place as a cornerstone of modern physics. In essence, this image serves as a powerful and direct visual proof of gravity's ability to warp the very fabric of space-time, a concept that once seemed purely theoretical. It represents a frontier where our current understanding of physics is stretched to its absolute limits, pushing us to explore new theoretical frameworks and refine our models of the universe. Ultimately, the black hole's shadow acts as a unique cosmic fingerprint, offering invaluable insights into the fundamental laws of nature that govern our universe. The release of the M87 image was a turning point for science and the public alike. For the first time, a black hole was transformed from theory into observable reality. The image matched Einstein's predictions perfectly, confirming general relativity and the strongest gravity ever tested. It opened new avenues of research, studying matter and magnetic fields in extreme environments. The ring's brightness reveals the black hole's spin and the behavior of infalling matter. For scientists, it's a treasure trove of data. For the public, it's a symbol of human curiosity. The image became an icon, inspiring millions and uniting people in awe. It shows that even the universe's greatest mysteries are within our reach. The first black hole image is both a scientific and cultural milestone. It inspires us to keep exploring the unknown. M87 isn't just a shadow, it's a cosmic engine. From its core, a colossal jet of plasma shoots out for over 5,000 light-years, powered by the black hole's spin and magnetic fields. This relativistic jet accelerates particles to nearly the speed of light, shaping the galaxy and its surroundings. The jet regulates star formation, blasting energy into the galaxy and sculpting its evolution. Studying the jet alongside the shadow is the next frontier for the EHT. In 2021, new images revealed the magnetic fields near the event horizon, supporting theories about jet formation. By observing M87 we're closing in on the secrets of how black holes launch these cosmic jets. The mystery of these engines is finally within our grasp. Imaging M87 opened a new window on the universe. We now see the effects of gravity itself on light, resolving structures at the scale of a black hole's event horizon. This is a new kind of astronomy, letting us test Einstein's theory in the most extreme conditions. The EHT's success is driving innovation, adding more telescopes, observing at new frequencies, and even planning space-based observatories. Soon we may see high-definition movies of black holes in action. The EHT has also imaged Sagittarius A*, the black hole at our galaxy's center, offering a direct comparison with M87*. This new window lets us explore both distant galaxies and our own cosmic backyard. The future of black hole astronomy is just beginning. The image of M87* is more than a scientific achievement, it changes how we see ourselves. It reminds us of our smallness in a vast universe, yet also of our ability to reach across cosmic distances with our minds and technology. The EHT project united people from around the world, showing what we can accomplish together. The same laws that govern black holes shape our everyday lives. The atoms in our bodies were forged in stars like those now feeding M87*. This image connects us to the cosmos and to each other. It's a story of ancient light and human curiosity, of exploring the unknown. The journey of discovery is far from over. We are part of this magnificent universe, and our adventure has only just begun. Imagine journeying billions of light years from home to a place of cosmic violence and creation. Our destination, the Phoenix Cluster, a colossal city of galaxies bound by gravity, glowing with the light of 1,000 billion suns. But at its heart lurks something monstrous, a supermassive black hole known as Cygnus X-1. Here, galaxies collide and merge, hot gas glows in X-rays, and the universe is still being forged. At the cluster's core, Cygnus X* reigns, a gravitational well so deep that not even light escapes. To grasp its scale, consider what a black hole truly is, matter compressed into an infinitesimal point, warping space-time itself. Its gravity is so intense, it draws in everything nearby, like a cosmic sinkhole. Cygnus X* is not just any black hole, it's one of the most extreme ever found. Our understanding comes from faint signals, light and radiation that have traveled nearly 6 billion years to reach us. Its existence challenges our models of how galaxies and black holes grow together. Cygnus X* forces us to ask new questions about the early universe and the forces that shape it. As we peer into the Phoenix cluster, we're looking back in time, witnessing a cosmic drama from before Earth was born. This is a place where the laws of physics are pushed to their limits. The Phoenix cluster is a laboratory for the universe's most powerful forces. And at its center, Cygnus X* stands as a reminder of the wonders and mysteries still waiting to be understood. The monster in the deep is real, and it's rewriting what we know about the cosmos. To understand Cygnus X*, we must first understand quasars, cosmic lighthouses outshining entire galaxies. Quasars were first detected as powerful radio sources that looked like faint stars, but they were far more energetic and distant. A quasar is the blazing core of an active galaxy powered by a supermassive black hole. As gas and dust spiral into the black hole, they form an accretion disk, one of the most violent places in the universe. Matter in the disk orbits at near light speed, heated to millions of degrees, glowing intensely. The light we see from a quasar is the final scream of matter before it vanishes forever. Quasars signal that a black hole is actively feeding. The brighter the quasar, the more voracious the appetite. By studying quasar light, astronomers estimate black hole mass, growth rate, and influence on their galaxies. The quasar at the heart of the Phoenix cluster first revealed the presence of Cygnus X*. It was a beacon from the distant past, alerting us to something extraordinary. Quasars are not just cosmic fireworks, they are signposts to the universe's most powerful engines. Cygnus A's quasar is among the brightest, marking it as a true monster. These beacons help us map the growth of black holes across cosmic time. And in Cygnus X*, we see one of the brightest, most extreme examples ever found. The Phoenix cluster, SPTCLJ 2344-4243, is a cosmic heavyweight, one of the most massive X-ray luminous clusters known. Located nearly 6 billion light-years away, it's a hub of gravitational power and intense activity. At its center, a galaxy is forming stars at a staggering rate, but even this is overshadowed by Cygnus X*. The cluster was discovered using the South Pole telescope, which detects shadows in the cosmic microwave background left by massive clusters. Follow-up observations revealed a vast cloud of hot gas, outshining all the stars in the cluster combined. Normally, a central black hole prevents this gas from cooling and forming new stars, but not here. In Phoenix, the gas cools rapidly, fueling both a starburst and the black hole itself. This anomaly pointed directly to Phoenix A's unique power. The usual feedback mechanism wasn't working. Something about this black hole was different. Its rapid growth and the cluster's starburst are intertwined, making Phoenix A** a cosmic oddity. The heart of the Phoenix cluster is a puzzle, and Phoenix A** is the key. The discovery of Phoenix A** began with a mystery, an unexpected torrent of star formation in the cluster's core. Normally, black holes suppress star birth, but here cold gas was flooding in, creating hundreds of new suns each year. Astronomers used Hubble, Chandra, and radio telescopes to study the quasar and the gas swirling around the black hole. They found gas clouds moving at incredible speeds, revealing a gravitational source of unprecedented mass. In 2012, Michael McDonald's team announced the discovery of a black hole far larger than predicted by standard models. Phoenix A** was not just supermassive, but ultramassive, estimated at over 20 billion solar masses and later even more. Its discovery forced astronomers to rethink how the universe's biggest black holes grow. Phoenix A's scale is almost beyond comprehension, about 100 billion times the mass of our Sun. That's the mass of a small galaxy, crushed into a region smaller than our solar system. For comparison, the Milky Way's central black hole is 4 million solar masses. Phoenix A** is 25,000 times more massive. Its event horizon spans nearly 600 billion kilometers, over 100 times the distance from the Sun to Pluto. If placed at our solar system's center, it would engulf every planet and more. Most black holes are a tiny fraction of their galaxy's mass, but Phoenix A** breaks this rule, dominating its environment. It's a gravitational anchor of unprecedented power. The sheer scale of Phoenix A** challenges our understanding of what's possible in the universe. It's a monument to the extremes of gravity and matter. Standing near it would be to witness the rawest power in the cosmos. Phoenix A** is not just big, it's in a class of its own. Its existence stretches the limits of physics and imagination. This is the true titan of the universe. Phoenix A** isn't just massive, it's growing at a staggering rate. Fueled by torrents of cooling gas, it devours matter equivalent to 60 suns every year. This rapid feeding powers its brilliant quasar, making it visible across billions of light years. The black hole's growth is so fast it overwhelms the usual feedback that would slow it down. Much of the cluster's cooling gas forms new stars, but a significant share feeds Phoenix A**. This runaway growth phase is rare in the local universe, but common in the early cosmos. Phoenix A** offers a glimpse into how the first supermassive black holes may have grown. We're witnessing a living relic of the universe's most dynamic era. Among black holes, Phoenix A** is a titan, outclassing even the universe's other heavyweights. The famous M87 black hole, imaged in 2019, is 6.5 billion solar masses. Phoenix A** is over 10 times more massive. Even Holm 15A's black hole, once thought enormous at 40 billion suns, is dwarfed by Phoenix A's 100 billion. Only a handful of black holes, like Ton 618, come close in mass. What sets Phoenix A** apart is its environment, a rich galaxy cluster actively feeding it, allowing us to study its growth in detail. While some titans are distant and shrouded in mystery, Phoenix A** is close enough for in-depth observation. It's not just a record holder, but a Rosetta Stone for understanding black hole growth. Phoenix A** sits at the very edge of what astronomers thought possible. Its existence forces us to rethink the limits of cosmic evolution. In the zoo of black holes, Phoenix A** is the ultimate outlier. Phoenix A* isn't just massive, it breaks the rules of cosmic evolution. Normally, a black hole's mass is a tiny, fixed fraction of its galaxy's bulge, suggesting a self-regulating growth. Phoenix A* shatters this pattern, outpacing its host galaxy by a huge margin. Its runaway growth hints that in certain environments, black holes can become true outliers. This challenges our understanding of how galaxies and black holes co-evolve. Did Phoenix A* start from an unusually massive seed, or did its environment fuel exceptional growth? Its existence pushes the limits of our theories, testing the boundaries of gravity and matter. Phoenix A** is a cosmic puzzle, rewriting the rules of the universe. Phoenix A* is just the beginning. Its mysteries will drive astronomy for decades. Future telescopes will let us peer deeper into its heart, mapping stars and gas near the event horizon. Each new observation will reveal more about its mass, spin, and history. Phoenix A* reminds us that the universe is dynamic, violent, and full of surprises. Studying such extremes teaches us about the forces that shaped everything, including ourselves. The future of black hole research is bright, focused on the darkest objects in the cosmos. Phoenix A* is a challenge, an inspiration, and a frontier. Its darkness lights the way to new cosmic discoveries. At the heart of our galaxy, in a region veiled from direct view, lies a place of unimaginable gravity. It's a realm where the laws of physics are stretched to their limits, a cosmic enigma that has captivated scientists for decades. This gravitational powerhouse is a supermassive black hole, a celestial behemoth known as Sagittarius A*. It's the anchor, the central point around which the entire Milky Way spins, dictating the movements of billions of stars and vast clouds of gas and dust. It plays a crucial role shaping the destiny of every star we see, influencing their orbits and their ultimate fate within the galactic tapestry. For centuries, the Milky Way appeared to us as a serene band of light stretching across the night sky, a gentle river of stars. But science revealed a far more dynamic reality, a swirling city of stars, a cosmic metropolis in constant motion, each star following its own path through the galaxy. Hidden behind thick veils of dust and gas, the galactic center, the heart of this metropolis, kept its secrets closely guarded. That is, until we developed new ways of seeing beyond the limitations of visible light, using telescopes that could pierce through the cosmic murk. What we found was not just a dense cluster of stars, a tightly packed stellar neighborhood, but the unmistakable gravitational signature of something far more profound, something truly extraordinary. Our Sun, a seemingly significant star to us, is just one of hundreds of billions of stars within the Milky Way, all orbiting this invisible giant, this central gravitational anchor. For decades, astronomers suspected a massive object resided at the heart of the galaxy, was holding the galaxy together, a gravitational linchpin, the keystone of the Milky Way's structure. Sagittarius A* is not just a curiosity, a strange anomaly in the cosmos. It's fundamental to the structure, the very architecture and evolution of the Milky Way, shaping its past, present, and future. Its story is a testament to human curiosity and ingenuity, unfolding over decades with telescopes that see the invisible, revealing the secrets hidden within the galactic core. We're about to journey to this incredible place, this cosmic heart, to explore what it is, its nature and properties, how we found it, the methods and instruments we used, and what it reveals about our universe, its fundamental laws, and its grand design. This is the story of the largest structures we know, the galaxies and clusters of galaxies that form the cosmic web, connected to the most extreme physics imaginable, the realm of black holes and warped space-time. Welcome to the heart of our galaxy, the enigmatic Sagittarius A*. So what exactly is Sagittarius A*? It's a supermassive black hole at the center of our galaxy, named for its location in the constellation Sagittarius. Unlike a star, it's a point of infinite density, a singularity where the laws of physics break down. Its defining feature is the event horizon, a boundary beyond which nothing, not even light, can escape. We can't see the black hole itself, only its effects on the space and material around it. The environment is chaotic. Stars packed tightly, gas and dust swirling in at incredible speeds, forming a superheated accretion disk. This disk glows in radio waves and X-rays, revealing the black hole's presence. When we talk about Sagittarius A*, we mean both the hidden black hole and the energetic region around it. It's the ultimate gravitational anchor, dictating the motion of everything in the Milky Way, including our Sun. Sagittarius A* is the silent, dark heart of our galaxy. Most black holes form from collapsing stars, but Sagittarius A* is in a different league. It's supermassive. It contains about 4 million times the mass of our Sun, packed into a space smaller than Mercury's orbit. Imagine compressing a dump truck full of sand into a single grain. That's the density we're talking about. No single star could create such a behemoth. These giants likely began as seeds in the early universe, growing by devouring gas, dust, and merging with other black holes. Their existence pushes the limits of physics, warping space-time, slowing time, and bending light. Sagittarius A** is a laboratory for testing Einstein's theory of general relativity. Its gravity shapes the entire galaxy, making it one of the most important objects for astronomers. Understanding its origins helps us unravel the history of galaxies themselves. It's not just massive, it's the Milky Way's gravitational heart, and it's still growing ever so slowly as the galaxy evolves. To truly grasp Sagittarius A's profound influence on our galaxy, we first need to understand its distance from us. This measurement serves as the cornerstone for much of what we can deduce about this enigmatic object. It's located approximately 27,000 light-years from Earth, a truly staggering distance when you consider the vastness of space. That immense separation means the light we observe emanating from the galactic center began its long journey towards us, when early humans were still expressing themselves through paintings on cave walls. Think about that for a moment. Therefore, every image we painstakingly capture with our telescopes is not just a snapshot, but a glimpse into the distant past. This vast gulf of space not only keeps us safely removed from the black hole's potentially disruptive chaos, but it also presents a significant challenge to astronomers striving to measure its distance with utmost precision. To overcome this, they rely on what are known as standard candles, stars possessing a known and consistent brightness. By carefully observing these celestial beacons, astronomers can effectively triangulate the galactic center's precise position in the sky. This measurement isn't just academic, it's absolutely crucial. It allows us to accurately convert what we observe in the sky, those seemingly tiny angles and movements, into real, tangible sizes and distances. And from there we can begin to accurately calculate the black hole's immense mass. When we meticulously observe stars as they whirl around Sagittarius A*, knowing the precise distance becomes paramount, allowing us to accurately determine their true orbital speeds and the shapes of their orbits. In fact, getting this distance measurement right was absolutely key to definitively proving the existence of a supermassive black hole lurking at our galaxy's heart. So the cosmic yardstick used to measure the distance to our galaxy's heart is now firmly and accurately set. It stands as a remarkable triumph of astronomical detective work, a testament to human ingenuity and perseverance, and ultimately it serves as the very foundation for virtually everything we currently understand about the enigmatic Sagittarius A*. How do you find something invisible? By looking for its effects. The story began in the 1930s when Carl Jansky detected a faint radio hiss from the center of the Milky Way. Decades later, astronomers pinpointed a compact, bright radio source, Sagittarius A*, at the galaxy's core. But the center is shrouded in dust, blocking visible light. Astronomers turn to radio and infrared telescopes, which can pierce the gloom. With these tools, they resolved individual stars near Sagittarius A*, for the first time. The breakthrough: if a supermassive black hole was there, its gravity would force nearby stars into rapid, unusual orbits. The stage was set to watch the stars dance around an unseen partner. By tracking their movements, astronomers could deduce the nature of the mysterious object. The hunt for the galaxy's heart was on. The ultimate proof came from watching stars orbit the invisible center. Two teams, led by Reinhard Genzel and Andrea Ghez, spent decades tracking stars near Sagittarius A*, with powerful infrared telescopes. They found stars whipping around at incredible speeds. One S2 completes an orbit in just 16 years. At its closest, S2 travels at 25 million kilometers per hour, about 3% the speed of light. Using the star's orbits, astronomers calculated the mass of the central object, 4 million times that of our Sun. The only thing that could be so massive and compact is a supermassive black hole. The orbits also showed the black hole's size, smaller than our inner solar system. No cluster of stars or exotic object could survive such close encounters. The silent waltz of these stars revealed the true identity of Sagittarius A*. In 2020, the Nobel Prize in Physics honored the scientists who revealed our galaxy's heart. Roger Penrose was recognized for proving black holes are a robust prediction of Einstein's theory. Reinhard Genzel and Andrea Ghez shared the prize for discovering the supermassive compact object at the Milky Way's center. Their work transformed Sagittarius A* from theory to reality. It required new technologies like adaptive optics to see through the blurring effects of Earth's atmosphere. Two independent teams using different telescopes reached the same conclusion, solidifying the discovery. The Nobel Prize celebrated not just individuals, but the power of patient, collaborative science. It was a triumph connecting deep theory with hard-won observation. Even with all the evidence, one thing was missing: a picture. Einstein's theory predicted a black hole should cast a shadow against its glowing accretion disk. Capturing this image required a telescope the size of Earth. Enter the Event Horizon Telescope, a global network of radio telescopes synchronized to act as one. After years of work, in 2022, the EHT team released the first ever image of Sagittarius A*. It showed a bright swirling ring of light surrounding a dark shadow, the black hole's silhouette. The image matched Einstein's predictions perfectly. For the first time, humanity gazed upon the edge of infinity at our galaxy's core. It was a technological and scientific marvel. The unseeable had finally been seen. Why should we dedicate our time and resources to studying this seemingly distant and enigmatic object? What makes it so important that scientists across the globe focus their attention on it? Because Sagittarius A* isn't just any black hole. It's our closest supermassive black hole, residing at the very center of our Milky Way galaxy. This proximity makes it a unique laboratory for unraveling cosmic mysteries, offering an unparalleled opportunity to probe the extreme physics near a black hole. Nearly every large galaxy in the universe is believed to host a supermassive black hole at its core. But Sagittarius A* is special. It's the only one we can study in such exquisite detail, allowing us to observe phenomena that would be impossible to discern in more distant galaxies. It helps us understand the intricate relationship between galaxies and the supermassive black holes they harbor, shedding light on how these behemoths grow and evolve together over cosmic timescales. Are they partners in a cosmic dance, each influencing the other's evolution? Or does one lead the way, with the black hole dictating the galaxy's fate, or vice versa? The properties of Sagittarius A*, such as its mass, a staggering 4 million times that of our Sun, its spin, which affects how matter spirals into it, and its surprisingly quiet state compared to other active galactic nuclei, are all crucial pieces of the puzzle when it comes to testing and refining our theories of galaxy evolution. Furthermore, it's the perfect cosmic laboratory to rigorously test Einstein's theory of general relativity. We can observe how space and time behave under these extreme conditions where gravity reigns supreme. By meticulously tracking the orbits of stars that whiz around Sagittarius A* at incredible speeds, and by analyzing the black hole's shadow, we can search for subtle deviations from Einstein's predictions, potentially uncovering hints of new physics beyond our current understanding. This might even lead us to a quantum theory of gravity, a long-sought-after framework that unifies general relativity with quantum mechanics. In essence, studying Sagittarius A* is akin to studying our own galactic origin story, peering back in time to understand how the Milky Way came to be. It connects us to the grand tapestry of the universe, revealing our place within the cosmic web. Our planet, a pale blue dot in the vast expanse; our Sun, the star that gives us life; our galaxy, a swirling island of stars, all held together by this silent giant, this enigmatic black hole at the center. It inspires us to look up at the night sky with wonder, challenges our technology to reach new heights of precision and sensitivity, and pushes the boundaries of knowledge, forcing us to rethink our understanding of the universe. Even in the darkest corners of the cosmos where mysteries abound, there are wonders waiting to be discovered, waiting for us to unlock their secrets. And at the heart of it all, at the very center of our galaxy, Sagittarius A* reminds us how much more there is to learn, how much more there is to explore, and how much more we can achieve when we dare to look deeper into the unknown. Out in the vast cosmos where galaxies swirl and stars ignite, there exists a realm of unimaginable scale and mystery. It's a place where the familiar laws of physics often take a back seat to the bizarre and the extraordinary. Among the countless constellations that adorn the night sky, the constellation Cygnus the Swan gracefully glides along the luminous band of the Milky Way. Its elegant form, traced by bright stars, has captivated stargazers for millennia. But hidden within this celestial swan, concealed from casual observation, is something truly extraordinary, a cosmic enigma that challenges our understanding of the universe. It's a place where the very fabric of space and time is warped and twisted, a region where the laws of physics as we know them seem to break down and yield to the ultimate force of gravity. This is Cygnus X-1, a name that resonates with profound implications for astrophysics. It is the first confirmed stellar mass black hole, a discovery that sent ripples through the scientific community. This groundbreaking discovery irrevocably changed our understanding of the universe and the exotic objects that populate it. But why should we care about something so distant, so seemingly detached from our everyday lives? Because Cygnus X-1 serves as irrefutable proof that the universe is far stranger, more complex, and more awe-inspiring than we could have ever imagined. Its discovery is not just a scientific achievement, it's a testament to human curiosity, a story woven with threads of initial skepticism, rigorous investigation, and ultimately profound revelation. Imagine a massive star, far larger and more luminous than our own sun, reaching the inevitable end of its stellar life. With its nuclear fuel exhausted, the star collapses catastrophically under the immense weight of its own gravity. The core implodes, crushing matter to unimaginable densities, ultimately forming a singularity, the heart of a black hole. This object's gravitational pull is so incredibly intense, so overwhelmingly powerful that nothing, not even light itself, can escape its relentless grip. Cygnus X-1 is the lurking monster, the gravitational behemoth residing at the very heart of the Swan constellation. Studying this enigmatic object has pushed the boundaries of our knowledge, forcing us to the very edge of what we consider reality. It has challenged our fundamental ideas about the nature of space itself, the flow of time, and the ultimate composition of matter. By painstakingly unlocking its hidden secrets, by deciphering the whispers from this cosmic abyss, we have come to realize that black holes are not merely theoretical constructs, mathematical curiosities confined to textbooks. They are, in fact, vital and dynamic components of the grand cosmic ecosystem, playing a crucial role in the evolution of galaxies. The story of Cygnus X-1, the tale of this stellar mass black hole, is the story of how humanity first confronted, how we first grappled with the truly mind-bending, often unsettling, but ultimately awe-inspiring nature of our universe. It's a journey of discovery that began with a simple yet profound question. Could such monstrous objects, these cosmic predators, these stellar mass black holes, really exist in the vast expanse of space? And it culminates with a resounding and undeniable, awe-inspiring yes, they do. To understand Cygnus X-1's impact, we travel back to the early 1960s. Einstein's general relativity predicted something bizarre. If enough mass is packed into a small space, gravity could punch a hole in reality, a black hole. Even Einstein doubted such objects could exist. For decades, black holes were just mathematical curiosities, invisible and undetectable. How do you find something that emits no light? Telescopes saw only what shone. The idea of a dark, massive object seemed impossible. Black holes remained a fringe idea, with no one actively searching for them. The tools of astronomy were built to capture light, not absence. Finding a black hole would require a new way of seeing the universe. It would take a technological leap and a new kind of astronomy. The stage was set for a revolution. The universe was about to reveal one of its deepest secrets, and it would all begin with a scream in the X-ray sky. The real breakthrough, the moment our understanding of the cosmos truly shifted, came with the birth of X-ray astronomy. It was a pivotal moment, opening our eyes to a universe far more energetic and violent than we had ever imagined. Back in the 1960s, pioneering scientists began launching rockets carrying X-ray detectors, instruments designed to capture the high-energy radiation that is otherwise blocked by our atmosphere. These rockets pierced Earth's protective atmosphere, venturing into the realm where cosmic radiation reigns, revealing a hidden, violent universe that had been previously invisible to us. It was like discovering a whole new world right next door. Then, in 1964, Riccardo Giacconi's team, driven by scientific curiosity and a thirst for the unknown, launched a rocket on a mission to detect these elusive X-rays. And what they found was astonishing. Their instruments detected a powerful X-ray source in the constellation Cygnus, a source they named Cygnus X-1. It wasn't just any X-ray source, it was one of the brightest X-ray sources ever found, blazing with an intensity that challenged existing theories. But the big question loomed: what exactly was it? Early data revealed that this source emitted immense energy, far exceeding what could be produced by normal, run-of-the-mill stars. It was something far more exotic and powerful. As more observations were made, the X-ray sky revealed the presence of neutron stars, the expanding remnants of supernova explosions, and hinted at the existence of perhaps something even stranger, something that defied easy explanation. Then, the launch of the Uhuru satellite in 1970 marked a turning point, changing everything we knew about the X-ray universe. Uhuru, the first dedicated X-ray astronomy satellite, meticulously mapped the X-ray universe in unprecedented detail, providing a comprehensive view of these high-energy phenomena. And crucially, Uhuru found that Cygnus X-1 signal flickered chaotically, exhibiting rapid variations on millisecond timescales. This rapid flickering provided a vital clue, suggesting that the source was incredibly small. Its size was estimated to be no larger than a few hundred kilometers across. Only a compact, incredibly powerful object, something with immense density, could behave in such a way, emitting such rapid and intense bursts of energy. The accumulating evidence pointed to something truly extraordinary, something that challenged the boundaries of our understanding. Cygnus X-1 was acting as a beacon, signaling the presence of a new kind of cosmic monster lurking in the depths of space. And with these new findings, the hunt to identify this mysterious object was officially on. The universe, in its enigmatic way, had given us a tantalizing clue. Now it was up to us, the scientists and astronomers, to piece together the puzzle and solve the mystery of Cygnus X-1. And the answer, when it finally came, would not only solve the mystery of Cygnus X-1, but would also fundamentally change our understanding of the universe and everything within it. The discovery of a compact yet incredibly powerful X-ray source emanating from the constellation Cygnus sparked intense debate among astronomers. It was an enigma that challenged existing theories and pushed the boundaries of our understanding of the cosmos. Was Cygnus X-1 a neutron star, a super-dense remnant of a collapsed star, packing immense mass into a tiny volume? These stellar corpses are known for their extreme properties and energetic emissions. Or was it something even more exotic and mind-bending? A black hole, an object with gravity so intense that nothing, not even light, can escape its grasp. The very idea was revolutionary. Neutron stars are dense remnants of massive stars formed in the cataclysmic explosions known as supernovas. They represent one possible endpoint in the life cycle of a star. But could these incredibly dense objects, neutron stars, truly explain the sheer power and intensity of Cygnus X-1's X-ray emissions? The question lingered in the minds of scientists. The alternative, a black hole, a concept once relegated to theoretical musings, now a potential explanation for this cosmic puzzle. A black hole, relentlessly siphoning gas from a nearby companion star in a cosmic dance of destruction and creation. As the gas spirals inward, it forms a superheated accretion disk, a swirling vortex of matter glowing intensely in X-rays, just before it disappears forever beyond the event horizon. This model, with its elegant explanation of the X-ray source, seemed to fit the observations, aligning with the data collected from telescopes around the world. Yet, despite its appeal, definitive proof remained elusive, hidden behind the vast distances and inherent challenges of observing such extreme phenomena. The debate surrounding Cygnus X-1 became legendary within the scientific community, a testament to the power of scientific inquiry and the pursuit of knowledge. The intensity of the discussion even sparked a famous, light-hearted wager between two giants of theoretical physics, Stephen Hawking and Kip Thorne, solidifying its place in scientific history. The problem was that both models, the neutron star and the black hole, could plausibly explain the observed X-ray emissions, making it difficult to distinguish between them based on X-ray data alone. The key to unlocking the mystery lay in finding and carefully studying the companion star, the celestial partner locked in a gravitational embrace with the unseen object. By meticulously tracking and analyzing its motion, astronomers hoped to indirectly reveal the properties of its mysterious companion. If astronomers could precisely measure the star's orbit, determining its speed and period, they could gain crucial insights into the system's dynamics. From the orbital parameters, they could then calculate the mass of the invisible object using the laws of gravity as their guide. The calculated mass would be the ultimate deciding factor, revealing its true nature and settling the debate once and for all. And so, the intensive search for the elusive companion star began, a quest that would push the limits of observational astronomy. It was a race against time and against other researchers, all vying to be the first to find the smoking gun that would finally solve the mystery of Cygnus X-1. Only then, with the mass of the unseen object firmly established, could the long-standing mystery of Cygnus X-1 be definitively solved. The answer, it turned out, lay hidden within the intricate dance of two stars, locked together in a gravitational ballet across the vast expanse of space. And the universe, after guarding its secret for so long, was finally about to give up its prize, revealing the true identity of Cygnus X-1. The final test, the crucial observation that would either confirm or refute the black hole hypothesis, was about to begin, ushering in a new era of understanding. Astronomers scanned the sky for the companion to Cygnus X-1. In 1971, two teams identified a massive blue supergiant HDE 226868 as the likely partner. Something was odd. The star wasn't still. Spectroscopy revealed its light shifted back and forth, a sign it was orbiting an unseen companion. Every 5.6 days, the star completed a cycle, locked in a gravitational dance. This was the breakthrough. By measuring the star's speed and orbital period, astronomers could calculate the mass of the invisible object. Newton's laws provided the tools. The faster the star moved, the more massive its partner had to be. The stage was set for a decisive calculation. The answer would settle the debate. Was Cygnus X-1 a neutron star or the first confirmed black hole? The universe was about to reveal the truth. The calculations were clear and stunning. Cygnus X-1's invisible companion had a minimum mass of 6 times our Sun. This was far above the maximum mass a neutron star could have, about 3 solar masses. Beyond that limit, nothing can stop collapse. Only a black hole fits. White dwarfs and neutron stars have limits, but Cygnus X-1 exceeded them all. The object was too massive, too dark, and too compact to be anything else. The evidence was overwhelming. The ghost from Einstein's equations was real. Cygnus X-1 was a black hole, orbiting a blue giant 6,000 light-years away. The debate was over. The first black hole had been found. A new era in astronomy had begun. The universe had revealed one of its most profound secrets. The point of no return was real, and we had found it. Cygnus X-1 became the prototype for all black holes to come. The cosmos would never look the same. The confirmation of Cygnus X-1 as a black hole was a turning point in science. For the first time, a theoretical object became a physical reality. Black holes moved from speculation to central players in astronomy. The discovery provided a blueprint for finding more. Look for a visible star orbiting an unseen, massive companion with strong X-rays. Hawking conceded his famous bet with Thorne, a testament to science's self-correcting nature. Cygnus X-1 became the benchmark for black hole research. The universe had spoken, and we were finally listening. Cygnus X-1's discovery opened the door to black hole astronomy. We learned that the universe's most powerful objects are often invisible. Dozens of stellar mass black holes have since been found, along with supermassive ones at galactic centers. The techniques pioneered with Cygnus X-1 changed how we study the cosmos. Black holes became laboratories for testing the limits of physics. In 2015, LIGO detected gravitational waves from merging black holes, confirming Einstein's predictions. This new era of astronomy stands on the shoulders of Cygnus X-1. It all began with a flicker in the Swan. Today we know Cygnus X-1's black hole is about 21 times the mass of our Sun. We can map its accretion disk and see jets blasting from its poles. Cygnus X-1 transformed from a mystery to a dynamic astrophysical system. Its legacy, black holes shape galaxies and drive cosmic evolution. The story of Cygnus X-1 is a testament to human curiosity and discovery. It shows how we learn to see the invisible and prove the existence of the unimaginable. Next time you look at Cygnus, remember the hidden monster within. Cygnus X-1 is a monument to our quest to understand the universe. There are places in the universe, vast and unexplored, where the rules as we know them, the very laws of physics, simply break down. These are the cosmic anomalies that challenge our understanding. These are points of infinite density, compressed matter beyond comprehension, and unimaginable gravity, black holes, the ultimate gravitational sinkholes. They're not just objects, massive and mysterious, but cosmic enigmas, defying our intuition and pushing the boundaries of knowledge, the ultimate expression of gravity's power, a force so strong it warps the very fabric of space-time. Black holes are a frontier of our understanding, a cosmic puzzle we are constantly trying to solve, where the fabric of reality is stretched to its breaking point, a place where light itself cannot escape. We're drawn to them, captivated by their mystery, because they represent the ultimate unknown, the great cosmic question mark, a place from which no information can return, a one-way ticket to oblivion. But how do you find something invisible? How do you detect the undetectable? You can't see a black hole directly. They are the masters of disguise. So we look for their influence, the subtle whispers of their presence on nearby stars and matter, the cosmic dance they orchestrate. We search for stars orbiting empty points in space, seemingly defying gravity's pull, or for intense radiation, the death cries of matter, from material being pulled into the abyss, a cosmic whirlpool of destruction. Each black hole we find, each piece of the puzzle we uncover, helps us test Einstein's theories, pushing the limits of our understanding of gravity and understand the life cycle of stars and galaxies, their birth, life, and ultimate fate. They're not just curiosities, mere oddities in the vast cosmos. They're laboratories for the most extreme physics in the universe, the ultimate testing ground for our theories. Black holes beckon us to look closer, to delve deeper into the mysteries of the cosmos and question everything we know about reality, to challenge our assumptions and expand our horizons. Deep within the sprawling tapestry of the night sky, nestled in the constellation Monocerotis, the unicorn, a celestial wonder awaits our discovery. It lies hidden from plain sight, a remarkable object. V616 Monocerotis, a name that might not immediately ring a bell, but one that holds a significant place in the history of black hole research. This enigmatic object is also catalogued as a 062000, a designation used by astronomers to keep track of its existence. For decades, it was celebrated as the closest known black hole to Earth, a claim that sparked the imagination of scientists and space enthusiasts alike. It was thought to be a cosmic neighbor lurking nearby, relatively speaking, in the vast expanse of the universe. Its apparent proximity made black holes feel less abstract and more real, transforming them from theoretical concepts into tangible objects of study. It presented itself as a specimen we could study in detail, offering a unique opportunity to unravel the mysteries surrounding these gravitational behemoths. V616 Monocerotis quickly became a local celebrity in astronomy, capturing the attention of researchers and the public alike. It served as a touchstone for understanding these dark titans, helping scientists to refine their models and theories about black hole formation and behavior. While closer black holes have since been found, pushing V616 Monocerotis down the list, its legacy remains, forever etched in the annals of astronomical history. It was the first to make the mind-bending reality of these cosmic vacuum cleaners, of black holes accessible, transforming them from abstract concepts into objects of scientific observation. V616 Monocerotis invited scientists to probe its secrets using cutting-edge telescopes and innovative techniques. It spurred the development of new astronomical techniques and detection methods, enabling us to find others lurking in the darkness. Its story is about a shift in our perception, a fundamental change in how we understand the universe. It represents the moment the invisible became detectable, when we gained the ability to see the unseeable. This black hole opened a new chapter in our exploration of the cosmos, paving the way for countless discoveries. Sometimes the universe's greatest mysteries are waiting right next door, hidden in plain sight, challenging us to look closer and unravel their secrets. V616 Monocerotis is a stellar mass black hole born from the collapse of a massive star. It contains about 6.6 times the mass of our Sun, crushed into a point smaller than a city. Its event horizon is only about 40 kilometers across, a mind-boggling concentration of mass. Located roughly 3,500 light-years away, it's distant yet close enough for detailed study. In the vastness of the Milky Way, that's practically our local area. Its combination of mass and size and proximity makes it scientifically invaluable. We can observe its effects on its surroundings in ways impossible with more distant black holes. V616 Monocerotis is a natural laboratory for exploring the universe's most extreme laws. The secret to finding V616 Monocerotis is that it's not alone, it's part of a binary system. Specifically, it's an X-ray binary, locked in a gravitational dance with an orange dwarf star. The companion star's motion reveals the presence of a massive, unseen partner. The black hole's gravity pulls material from the star, creating a dramatic interaction. This process generates intense X-rays, a beacon our telescopes can detect. The binary system acts as a cosmic signpost pointing to the hidden black hole. The visible star's orbit and the X-ray flares are key clues. Without this partnership, V616 Monocerotis would likely have remained unknown. Its existence as an X-ray binary unlocked its discovery. This system lets us study one of the universe's most mysterious objects in detail. The X-rays from V616 Monocerotis come from a process called accretion. The black hole siphons material from its companion, forming a spinning, superheated accretion disk. Gas in the disk swirls at incredible speeds, heating up to millions of degrees. This hot gas emits intense X-ray radiation, making the system visible to our telescopes. The accretion disk isn't always stable. Irregular flows can cause dramatic X-ray outbursts. During these flares, the system becomes one of the brightest X-ray sources in the sky. Studying these flares gives us insight into the chaotic physics near black holes. The accretion disk acts as a cosmic billboard, advertising the black hole's presence. It converts gravitational energy into light with remarkable efficiency. While the black hole itself is dark, its surroundings are among the brightest places in the universe. The story of V616 Monocerotis, a celestial object that would later be recognized as a black hole binary system, began in 1975. It's a tale of serendipity, keen observation, and the relentless pursuit of understanding the universe's most enigmatic objects. It all started when the Ariel 5 satellite, a pioneering spacecraft dedicated to X-ray astronomy, detected a massive and unexpected X-ray outburst emanating from a previously unremarkable region of the sky. An object previously unseen and uncatalogued suddenly became the brightest X-ray source in the entire sky, capturing the attention of astronomers worldwide. This dramatic event signaled the birth of a new mystery. Astronomers, alerted by the satellite's findings, quickly turned their optical telescopes to the precise coordinates and found a faint star, previously lost in the background noise, that had also undergone a significant brightening, mirroring the X-ray outburst. The simultaneous flare in both X-rays, a high-energy form of light, and visible light strongly suggested the presence of a binary system where two celestial objects are gravitationally bound and orbiting a common center of mass. Initially, the outburst led astronomers to believe they were witnessing a nova, a stellar explosion, but the sheer intensity and unusual characteristics of the X-rays hinted at something far more extreme and exotic than a typical nova event. After the initial outburst gradually faded, astronomers meticulously measured the star's motion over time and found that it was orbiting a dark, unseen companion, completing one full orbit approximately every 7.75 hours. The star's rapid wobble, a telltale sign of orbital motion, revealed the presence of a massive yet invisible companion exerting a strong gravitational pull. Through careful astronomical calculations and analysis of the star's orbital parameters, scientists determined that the unseen object had to possess a mass at least 3.5 times greater than the mass of our Sun. This mass range ruled out the possibility of it being a neutron star. the densest object known in the universe besides black holes. The only remaining explanation, the one that fit all the observed data, was a stellar mass black hole, an object with gravity so intense that nothing, not even light, can escape its grasp. This discovery marked a pivotal moment in astrophysics, solidifying V616 Monocerotis as one of the first confirmed black hole candidates. And for many years following its identification, it held the distinction of being the closest known black hole to our own planet, Earth. The incredible hunt, driven by scientific curiosity that began with a seemingly random flash of X-rays in the vast expanse of space, ultimately ended with the unmasking of a hidden monster, a stellar mass black hole lurking in our galactic neighborhood. V616 Monocerotis, therefore, became a landmark discovery, a crucial stepping stone in our understanding of black holes and their role in the cosmos. Its story serves as a powerful testament to the remarkable power of astronomical observation, careful deduction, and the unwavering human desire to unravel the mysteries of the universe. V616 Monocerotis quickly became a foundational object for studying stellar mass black holes. It's a clear nearby example with all the key components: a black hole, a companion star, and an accretion disk. Researchers use it as a model for how black hole binaries work. Its X-ray flares and orbital data allow us to test theories directly. Even in its quieter state, the system provides invaluable data on accretion and black hole behavior. It's the benchmark against which new black hole discoveries are measured. V616 Monocerotis transformed black holes from theoretical oddities into concrete, vibrant research subjects. It was the right object in the right place at the right time. Studying V616 Monocerotis is a triumph of modern astronomy using instruments across the electromagnetic spectrum. X-ray satellites like Ariel 5, Chandra, and XMMM Newton revealed the hot accretion disk. Ground-based optical telescopes measured the companion star's motion, confirming the black hole's mass. Radio telescopes detected powerful jets launched from the system during outbursts. Each wavelength reveals a different piece of the puzzle. X-rays show the disk, optical light the star, radio waves the jets. Only by combining all these observations can we understand the full story. It's a beautiful example of technology working in concert to unveil the invisible universe. V616 Monocerotis shows how global collaboration and diverse tools are essential for discovery. The system's secrets are revealed by the synergy of space and ground-based science. Half a century after its discovery, V616 Monocerotis remains a subject of intense scientific interest. Its legacy is as a pioneer and a perfect laboratory for black hole research. Scientists still monitor its faint state, searching for new clues about accretion and gravity. The questions have evolved, from proving its existence to probing the details of black hole physics. For the public, it's a symbol of the wonders hidden in our cosmic neighborhood. V616 Monocerotis bridges the gap between complex science and human curiosity. It taught us how to find the invisible and interpret the violent language of X-ray outbursts. Even in darkness, it continues to illuminate our understanding of the universe. In the cosmos, some places push the laws of physics to their breaking point. Matter is crushed into a point so dense that not even light can escape. These are black holes. Born from the collapse of massive stars, black holes are the universe's ultimate enigmas. For years, they existed only in theory, hidden in Einstein's equations. But then we found them. By watching stars orbit invisible points, and by detecting powerful jets from galactic centers. Black holes aren't just cosmic curiosities, they shape galaxies and drive cosmic evolution. Each discovery peels back another layer of the universe's mysteries. We hunt for them with advanced instruments, searching for the gravitational fingerprints they leave on their surroundings. The search has revealed a universe stranger than we imagined, filled with these silent, powerful objects. And sometimes the hunt leads us to a black hole right in our own galactic neighborhood. These discoveries remind us the universe is more mysterious and more beautiful than we ever dreamed. Every black hole we find is a clue to the life and death of stars and the fabric of space-time itself. They are not just destroyers but creators, shaping the cosmos on the grandest scales. And now we've found one closer than ever before. For years, the closest known black hole was thought to be thousands of light years away, but the universe surprised us. Using data from the Gaia mission, astronomers found Gaia BH1, the closest confirmed black hole to Earth. It's just 1,560 light-years away in the constellation Ophiuchus, 3 times closer than the previous record holder. Gaia BH1 is a stellar mass black hole about 10 times the mass of our Sun, yet only a few dozen kilometers across. Despite its power, it's completely invisible. No light, no X-rays, just silent gravity. Its discovery was a triumph of precision astronomy. Gaia BH1's proximity suggests our galactic neighborhood may be filled with many more hidden black holes. For every one we find, there could be dozens more lurking unseen. This discovery forces us to rethink how common black holes are in our own backyard. We didn't find Gaia BH1 by looking for explosions or bright flares. Instead, we detected a subtle wobble in a sun-like star, a tiny clue that revealed a massive invisible companion. Gaia BH1 was hiding in plain sight, its presence betrayed only by its gravitational pull. This is science at its best, patient, precise, and transformative. Our neighborhood is far more interesting and mysterious than we ever imagined, and Gaia BH1 is just the beginning. We often picture black holes as cosmic monsters devouring everything nearby in a blaze of X-rays. But Gaia BH1 is different, it's dormant. There's no glowing accretion disk, no jets, no radiation. It's silent and invisible. Gaia BH1 drifts through space, its gravity immense, but with nothing nearby to consume. It's part of a binary system, paired with a sun-like star at a safe distance, too far for the black hole to steal material. The star is untouched, and the black hole is starved of fuel. This dormancy is why Gaia BH1 remained hidden for so long. Most black holes in the universe are likely dormant, invisible to traditional detection methods. Finding Gaia BH1 means we're finally learning to spot these silent giants. Dormant black holes could be everywhere, quietly shaping the galaxy. Gaia BH1 is our first glimpse into this hidden population. The universe is full of sleeping giants waiting to be found. To understand Gaia BH1, we need to distinguish between active and dormant black holes. Active black holes are cosmic showmen, feeding on nearby matter, surrounded by bright, hot accretion disks and blazing in X-rays. These are the black holes we've known for decades, lighthouses of the universe, impossible to miss. Dormant black holes like Gaia BH1 are masters of stealth. They don't feed, don't glow, and emit no detectable radiation. They might be alone, or in wide binaries where their companion is too distant to be affected. Most stellar mass black holes in our galaxy are expected to be dormant. Our traditional searches focused on X-rays have only found the tip of the iceberg. Gaia BH1 is the first clear look at this silent majority. These hidden black holes have been shaping our galaxy all along. The discovery of Gaia BH1 marks a turning point in our understanding. We're finally seeing the unseen. The universe is far darker and richer than we realized, and the hunt has only just begun. How do you find an invisible black hole? You look for its influence. Astronomers focused on Gaia BH1's companion, a sun-like star. The star isn't being devoured, but it's locked in a gravitational dance with the black hole. From Earth, we see the star wobble, a tiny periodic motion caused by its massive unseen partner. Detecting this wobble required extraordinary precision. By measuring the star's orbit, astronomers calculated the mass of the invisible companion, about 10 times the Sun. Only a black hole could be that massive and that dark. This method, called astrometry, is a powerful tool for finding the unseen. It's the same technique used to discover exoplanets, now applied to black holes. Gaia BH1 was found not by a flash, but by patient, meticulous observation. We watched its dance partner and uncovered a cosmic giant. Sometimes the universe's biggest secrets are revealed by the smallest motions. Gaia BH1's discovery was only possible thanks to the Gaia spacecraft. Gaia's mission map over 1 billion stars in the Milky Way with unprecedented precision. It measures positions and motion so accurately it can detect a star's wobble from thousands of light years away. This precision lets Gaia spot the subtle dance of binary systems, revealing hidden partners, including black holes. Astronomers sift through Gaia's massive dataset, searching for stars with unexplained wobbles. When a candidate is found, ground-based telescopes measure its motion in detail, confirming the presence of an invisible companion. This synergy between space and ground-based observations is revolutionizing astronomy. Gaia wasn't designed to find black holes, but it's become one of our best tools for the job. We're now able to map the unseen universe, one wobbling star at a time. Gaia has opened a new window onto the cosmos. The hidden population of dormant black holes is finally within reach. The universe is revealing its secrets star by star. Gaia BH1's discovery marks a paradigm shift in black hole hunting. For decades, we relied on X-ray emissions, finding only the loud, active black holes. But most black holes are quiet, invisible, and missed by these methods. Astrometric detection changes everything. By tracking the gravitational pull on companion stars, we can now find the silent majority. There could be up to 100 million stellar mass black holes in the Milky Way, most dormant, like Gaia BH1. Until now, we'd found only a handful. This new method promises to uncover thousands more. Each discovery helps us build a true census of black holes in our galaxy. We can finally answer, how many are there? What are their masses? Where do they hide? Gaia BH1 is just the first of many. The unseen population is coming into view. Our understanding of the Milky Way is about to be rewritten. Gaia BH1 isn't just close and dormant. It challenges our theories of how black holes form in binary systems. A black hole of this mass should have formed from a massive star, which would have expanded and exploded as a supernova. But Gaia BH1's companion star orbits at a distance where it should have been engulfed or destroyed, yet the companion survives in a nearly perfect orbit. This suggests our models of binary evolution are incomplete. Maybe some massive stars collapsed directly into black holes, skipping the violent supernova. Gaia BH1 could be the first evidence for this quiet, direct collapse scenario. Alternatively, the black hole and star may have become a pair later through a chance encounter. Either way, Gaia BH1 forces us to rethink how black holes and their companions form. One discovery can upend decades of theory. The universe always has new surprises. Gaia BH1 reminds us that our cosmic neighborhood is full of surprises. The universe isn't static, it's dynamic, mysterious, and ever-changing. We're now mapping not just the stars we see, but the invisible giants that shape our galaxy. Each new discovery fills in the dark spaces on our cosmic map. Gaia BH1 shows that even close to home, there are hidden wonders. Precision astrometry is revolutionizing our view of the universe. We're living in a golden age of discovery, building a dynamic map of the cosmos. A dormant black hole nearby is a tangible link to the universe's most extreme physics. It's a relic of a star that lived and died before our solar system formed. Gaia BH1 enriches our understanding of home. It's a story of seeing the unseen, a triumph of curiosity and ingenuity. There are still fundamental discoveries to be made right here among familiar stars. Our cosmic backyard just got a lot more interesting. We live on a small blue world, a pale and fragile sphere suspended in the inky blackness. Adrift in a vast cosmic ocean, an endless expanse dotted with galaxies and mysteries. For millennia, we've looked up at the stars and wondered, our minds filled with questions. What is out there, lurking in the shadows beyond our solar system? What is our place in this universe, this grand and awe-inspiring cosmic tapestry? Our story is one of exploration, a relentless pursuit of knowledge driven by insatiable curiosity. We've built tools to extend our senses, reaching further than ever before, reading the light from distant galaxies to piece together the history and evolution of the cosmos. But light isn't the only messenger carrying secrets from the depths of space. There are stories written in the very fabric of reality, stories of unimaginable power, events so extreme they shake space and time, creating ripples that propagate across the universe. For centuries, these stories unfolded in silence, hidden from our view, whispers in a language we couldn't hear, a cosmic symphony beyond our comprehension. We were deaf to the universe's grandest symphonies, missing out on the most dramatic performances. Our understanding, as deep as it was, remained incomplete, a partial picture of a much larger reality. Imagine standing on a shore, seeing waves but never hearing the ocean's roar, feeling the spray but missing the depth of its power. That was our relationship with the universe, a visual experience lacking a crucial dimension. observers of a silent movie, captivated by the visuals but missing the immersive sound. We saw exploding stars, brilliant flashes of light across unimaginable distances and swirling galaxies, majestic cosmic whirlpools of stars and gas, but we couldn't hear the soundtrack, the underlying symphony of gravitational waves. The cataclysmic events shaping the universe, the collisions of black holes and neutron stars, were invisible to us, hidden behind a veil of silence. Our theories predicted them, our equations hinted at their existence, but witnessing one seemed a distant dream, a goal just beyond our reach. Then, one September morning, as the sun rose on a new day, everything changed and the universe began to sing. A message, traveling for over 1 billion years across the vast cosmic distances, finally arrived, not carried by light, but as a ripple in space-time, a gravitational wave. A vibration stretched and squeezed the universe, distorting the very fabric of existence, reaching our quiet planet, a gentle tremor in the cosmic ocean. This whisper was the sound of 2 black holes colliding, a cosmic dance of destruction and creation. For the first time, humanity was listening, tuning into the gravitational symphony of the universe. We had learned the language of gravity, unlocking a new way to understand the cosmos. A new window onto the cosmos had opened, revealing a universe far more dynamic and violent than we had ever imagined. The view was more spectacular than we had ever imagined, a breathtaking panorama of cosmic events. The universe was no longer silent, it was alive with the sounds of gravitational waves. We had joined the cosmic conversation, becoming active participants in the ongoing story of the universe. And the story was just beginning, with countless more whispers waiting to be heard. On September 14, 2015, a seemingly ordinary day, a signal arrived, a faint ripple in the fabric of space-time itself. It was detected by 2 incredibly sensitive machines, one nestled in the heart of Louisiana and the other in the evergreen landscapes of Washington. The signal was incredibly tiny, almost imperceptible, lasting less than 1/4 of a second, a fleeting moment in time, but it told a story of cosmic proportions. A story that had traveled across billions of light years. Scientists, with a mix of excitement and meticulousness, named it GW150914, a gravitational wave, a distortion in the very fabric of space and time, the first ever directly observed by humanity. It was the sound of the universe's most extreme event, a cataclysmic collision of unimaginable scale. LIGO, the Laser Interferometer Gravitational Wave Observatory, had detected a cosmic chirp, a low hum rising rapidly in frequency and intensity before abruptly stopping. This was the unmistakable signature of 2 black holes, spiraling together at incredible speeds, a cosmic dance of destruction, locked in a gravitational dance for eons, circling closer and closer. They sent out waves of energy, ripples that propagated across the universe as they finally merged into one. This event was completely invisible to every telescope ever created. Black holes, by their very nature, emit no light. To hear this collision, to sense it through gravitational waves, was to gain a new sense, as if a species born blind could suddenly see the vibrant colors of the world. Decades of painstaking theory and groundbreaking engineering led to this extraordinary moment. On that seemingly ordinary September morning, the universe, cutting-edge technology, and insatiable human curiosity converged in a symphony of discovery. The cosmic silence was finally broken. We heard the faint whisper, the echo of 2 giants colliding in the depths of space, 1 billion light-years away from our own world. Humanity had, at long last, tuned into a new cosmic channel, a new way of perceiving the universe. The broadcast from the cosmos had just begun, and the possibilities were endless. We were no longer just passive observers of the universe. We were active listeners, capable of hearing the universe's most profound secrets. The universe had spoken in a language we were only just beginning to understand, and we were ready, more than ever, to listen and to hear more of its incredible story. To understand GW150914, we must rethink space and time. For centuries we saw space as a fixed stage and time as a universal clock. Einstein shattered this view, revealing space and time as a single dynamic fabric space-time. This fabric bends and curves under mass and energy, gravity itself. Imagine a stretched rubber sheet. A heavy ball warps it and smaller objects follow the curve. Now disturb the sheet, move the ball, and ripples spread outward. These are gravitational waves, disturbances in space-time itself. Most objects create waves too faint to detect. Only extraordinary events, like black holes colliding, make waves strong enough to reach us. As two black holes orbit, they stir space-time, sending out waves at light speed. These waves carry energy away, drawing the black holes closer. The result, a cosmic crescendo, a rising symphony of space-time. When the final embrace comes, the universe itself rings. And now, for the first time, we can hear it. The black holes behind GW 150914 were titans, cosmic behemoths locked in an ancient gravitational embrace. One, a staggering 29 times the Sun's mass, the other, an even more immense 36 times. These were not your average stellar remnants. For millions upon millions of years, they circled each other in a silent, mesmerizing waltz, a slow dance dictated by the laws of gravity. But in their final, frantic moments, they orbited each other hundreds of times per second, a dizzying, accelerating spiral. Hurtling through space, they were moving at half the speed of light, a truly mind-boggling velocity. The energy released in this cataclysmic event was immense, almost incomprehensible in scale. For a brief fleeting instant, the merger outshone all the stars in the observable universe, a beacon of pure energy in the vast cosmic darkness. Then, with unstoppable force, they merged into one. The two became one singular entity, a new, even more massive black hole forged in the crucible of cosmic collision, forming a new black hole with a mass of 62 suns. But 3 solar masses were missing, seemingly vanished from existence. In reality, that missing mass was converted directly into pure energy, blasted outwards as powerful gravitational waves rippling through space-time. This was the faint chirp that LIGO, the Laser Interferometer Gravitational Wave Observatory, detected, space-time itself screaming in agony as it was violently torn apart and then reformed in the aftermath of the merger. The gravitational waves traveled for an incredible 1.3 billion years across the vast expanse of the cosmos, stretching and squeezing everything in their path, subtly distorting the very fabric of reality. By the time these ancient waves finally reached Earth, their effect was almost unimaginably minuscule. Distorting LIGO's massive arms by less than the width of a single proton, an almost impossible measurement. Yet against all odds, we heard it, a testament to human ingenuity and perseverance. We captured the faint echo of that titanic dance, a whisper from the distant past. The universe's most violent events had left their indelible mark on space-time, a mark we could now read, and we had finally learned to listen to the universe's symphony of gravitational waves. The cosmos had revealed a new and profound secret, unlocking a new way to understand the universe. A century before GW 150914, Einstein unveiled general relativity, a new vision of gravity. His equations predicted that massive, accelerating objects would create ripples in space-time, gravitational waves. Einstein doubted we'd ever detect them. The effect seemed impossibly small. For decades, gravitational waves were a mathematical ghost, a curiosity in the equations. Detecting them was like hearing a pin drop in a hurricane. The Earth is noisy, vibrating with earthquakes, ocean waves, even passing trucks. Yet the pursuit of knowledge drove generations of scientists and engineers. They built ever more sensitive detectors, undaunted by the challenge. The quest for gravitational waves became a great scientific adventure. Einstein gave us the map. It took a century to follow it, and finally we heard the universe's faintest whisper. GW 150914 was detected by LIGO. 2 observatories, one in Louisiana, one in Washington. Their separation is crucial. A real signal must arrive at both, ruling out local noise. Each LIGO detector is a giant L shape with 2 4-kilometer arms. A laser beam splits, travels down each arm, bounces off mirrors and recombines. Normally the beams cancel out and no light reaches the detector. But a passing gravitational wave stretches one arm, squeezes the other, knocking the beams out of sync. A tiny flicker of light is the signal, a ripple in space-time itself. The Virgo detector in Italy joined later, forming a global network. These instruments are the quietest places on Earth, built to hear the universe's faintest whispers. They are our planet's ears, tuned to the music of space-time. Detecting GW 150914 changed everything. For the first time, we could hear the universe, not just see it. Gravitational waves are a new sense, unblocked by dust, unimpeded by darkness. They carry information from the heart of the most violent events. We can now probe supernovae, witness neutron star collisions, and study black holes directly. This is more than a new telescope, it's a new way of observing. Like Galileo's first telescope, it opens a window to the unknown. We've entered the era of multi-messenger astronomy, combining light and gravity to build a fuller picture. When two neutron stars collided in 2017, we saw it in both gravitational waves and light. By combining these messengers, we understand the universe more completely. The silent movie now has a soundtrack, and the story is richer than ever. The first gravitational wave detection was just the beginning. Since 2015, LIGO and Virgo have heard dozens more events: black hole mergers, neutron star collisions. Each detection adds to our cosmic census, revealing how black holes form and how heavy elements like gold are created. The future is bright. New detectors on Earth and in space like LISA will hear even fainter signals. We'll map the dark side of the universe in unprecedented detail. We'll test Einstein's theory in the most extreme conditions. Surprises are certain. Every new window brings the unexpected. Gravitational wave astronomy is a new journey, deeper into the cosmos than ever before. We're just at the beginning. The universe's symphony is only starting to play. We are a curious species, driven to explore and understand. Gravitational waves are the latest chapter in our quest to know the cosmos. The universe tells its story in light and gravity. For most of history, we could only read part of that story. Now we can listen as well. We hear echoes of creation, collisions of worlds, the symphony of space-time. This new ability connects us to the universe in a profound way. We are not separate from the cosmos. We are part of it. What will we hear next? Perhaps the echo of the Big Bang or something entirely unexpected. The universe is full of wonders, and we've only just begun to listen. When we hear black holes merge 1 billion light years away, it's a message for all humanity. Through science and curiosity, we begin to understand the story is only just beginning. Imagine a place far removed from our everyday experiences, a realm where the familiar laws of physics bend and break. Imagine a place in the universe where gravity is so strong, so overwhelmingly powerful, that not even light, the fastest thing in the cosmos, can escape: a black hole. These enigmatic objects represent the ultimate cosmic trap. It's not a hole in the traditional sense, like a void or an opening, but an immense amount of matter, an incomprehensible quantity squeezed into an incredibly small space. Think of it as the ultimate cosmic compression. Picture the mass of our sun, a colossal ball of burning gas, crushed into a sphere just a few kilometers across, a space smaller than many cities, creating a gravitational pull that warps space-time itself, bending light and distorting our view of the universe. At the center lies a singularity, a point of infinite density, where the laws of physics as we know them cease to apply. This singularity is surrounded by the event horizon, the point of no return, the boundary beyond which nothing can escape the black hole's grasp. Anything crossing this boundary, from asteroids to stars, even entire planets, is lost forever, swallowed by the abyss. Black holes are born from the death of massive stars, the remnants of stellar giants when their cores collapse after a supernova, a spectacular explosion that marks the end of a star's life. If the core is heavy enough, possessing sufficient mass, it collapses beyond a neutron star, an already incredibly dense object becoming a black hole, a silent, invisible remnant, a testament to the power of gravity. But black holes aren't just cosmic vacuum cleaners, they're far more complex and dynamic than that. They shape galaxies, influence star orbits, and test the limits of physics, pushing our understanding of the universe to its very edge. By studying them with powerful telescopes and advanced instruments, we peer into the structure of space-time and the mysteries of the universe, unraveling the secrets of these cosmic enigmas. They challenge our understanding of reality and inspire endless wonder, driving us to explore the cosmos and question our place within it. Black holes are reminders of the vast, mysterious, and beautiful universe we inhabit, a universe filled with wonders beyond our wildest imaginations. And at the heart of our own galaxy, the Milky Way, one of these cosmic giants, a supermassive black hole known as Sagittarius A*, awaits discovery and continues to captivate our scientific curiosity. Deep in the heart of the Milky Way, shrouded in cosmic dust and mystery, lies a hidden giant, a behemoth of gravity and energy, Sagittarius A. It's a name that echoes through the halls of astrophysics. This supermassive black hole is not just any ordinary celestial object. It's the gravitational anchor of our entire galaxy, the Milky Way. It's the central point around which everything, including our own sun and the solar system we call home, revolves in a grand cosmic dance. Located approximately 27,000 light-years away from Earth, a distance that underscores the vastness of space, Sgr A is far from being just an ordinary black hole. It's something truly special. It contains an astounding mass equivalent to that of 4 million suns, all compressed into an incredibly small space. This immense mass is packed into a region that's actually smaller than the orbit of Mercury around our sun, a truly mind-boggling feat of cosmic compression. Its immense gravity exerts a powerful influence governing the complex and mesmerizing motion of billions upon billions of stars swirling around the galactic center. In fact, most large galaxies that we've observed throughout the universe also possess a supermassive black hole residing at their very core, suggesting a fundamental link between their growth and the overall evolution and development of the galaxy itself over billions of years. Therefore, gaining a deeper understanding of Sgr A* is absolutely key to unlocking the secrets of our own galactic history and unraveling the mysteries of how the Milky Way came to be. Despite its incredible power and the immense forces at play, Sgr A* poses absolutely no direct threat to us here on Earth, because its gravitational influence, while significant on a galactic scale, is minuscule and negligible at our vast distance from the galactic center. Instead, its relative proximity compared to other supermassive black holes makes it an absolutely perfect subject for detailed scientific study and observation, transforming it into a unique and invaluable cosmic laboratory for researchers around the world. It provides us with an extraordinary opportunity to rigorously test our current theories of gravity and to probe the complex physics of black holes in unprecedented detail, all from a relatively close vantage point. Indeed, Sgr A* holds the distinction of being the closest supermassive black hole to our planet Earth, thereby offering unparalleled and exciting opportunities for groundbreaking scientific discovery and a deeper understanding of the universe. In essence, it serves as our window, providing a direct view into the very heart of the Milky Way galaxy, allowing us to explore the mysteries that lie within. The hunt for Sagittarius. A* was a scientific detective story. In the 1970s, astronomers detected a bright, compact radio source at the Milky Way's center, Sagittarius A*. They couldn't see the black hole directly, but its effects on nearby stars were unmistakable. Two teams, led by Reinhard Genzel and Andrea Ghez, tracked stars orbiting close to the galactic center. They observed stars moving at thousands of kilometers per second, with one, S2, completing an orbit in just 16 years. These rapid orbits could only be explained by an immense, invisible mass. Calculations revealed a compact object with 4 million times the mass of our sun. The only explanation, a supermassive black hole. This work earned Genzel and Ghez the Nobel Prize in Physics in 2020. Their discovery provided definitive proof of Sagittarius A's existence. Sagittarius A* stands out as a truly exceptional object among the diverse population of supermassive black holes scattered throughout the cosmos. Its characteristics are quite distinct, setting it apart from its more boisterous and energetic counterparts. What makes it so special? It's largely due to its quiet nature. Unlike the blazing cores of many galaxies, which are powered by intensely active supermassive black holes, our black hole, Sagittarius A*, is relatively dormant. It's not consuming vast amounts of material. Instead, it feeds on only a trickle. This quiescent behavior makes the Milky Way's center appear dim and relatively unremarkable compared to active galaxies, where the central black holes are voracious consumers, outshining all the stars in their host galaxies combined. Imagine for a moment if Sgr A* were more active, constantly pulling in matter and emitting tremendous amounts of radiation. The night sky would be dramatically different, and perhaps more significantly, life on Earth might not have emerged, as such intense radiation could be detrimental to the development of life. Therefore, its calmness isn't just an astronomical curiosity, it's a scientific gift, allowing us to study it in detail. The relative dimness of Sgr A* allows us to observe regions incredibly close to the event horizon, the point of no return where gravity's effects are not just strong but truly extreme, warping space-time in ways that challenge our understanding of physics. In contrast, more active galaxies possess brilliant accretion disks, swirling masses of superheated gas and dust, which unfortunately obscure these crucial regions from our direct view. Scientists are still working diligently to unravel the mystery of why Sgr A* is so quiet and well-behaved. Perhaps it's simply starved of fuel, residing in a region of space where there's a lack of available material to consume. Or perhaps, even when material gets close, it is flung away in powerful jets and outflows before it can be consumed by the black hole. Whatever the underlying reason, this gentle giant offers us a rare and exceptionally clear view of a supermassive black hole in action, or rather, relative inaction. It serves as a pristine laboratory, a natural testbed for rigorously testing our fundamental understanding of gravity, the very fabric of space-time, and the exotic physics that govern these extreme environments. By studying Sgr A's unique character and its unusual behavior, we can continue to probe the universe's deepest mysteries and push the boundaries of our knowledge. Sagittarius. A* is the gravitational heart of the Milky Way, anchoring the galaxy's rotation. Every star, including our Sun, orbits this central point over millions of years. Sgr A* also regulates the galaxy's growth through a process called galactic feedback. In the past, it likely unleashed powerful winds and jets, shaping star formation by blowing away gas. This self-regulation explains why galaxies don't grow endlessly and why the largest galaxies have the biggest black holes. Evidence of past eruptions, like the Fermi bubbles, lingers in the galaxy's structure. Studying Sgr A* reveals the intertwined history of our black hole and the Milky Way. Understanding it means understanding the life cycle of our entire galaxy. Sagittarius A* is the ultimate testbed for Einstein's general relativity. The intense gravity near Sgr A* warps space-time, letting us test the theory in extreme conditions. Stars like S2 orbiting close to the black hole reveal subtle effects predicted by relativity. In 2018, astronomers measured gravitational redshift in S2's light, matching Einstein's predictions. They also observed Schwarzschild precession, the slow rotation of S2's orbit, again confirming relativity. These results show Einstein's theory holds even near a supermassive black hole. As technology improves, we'll track stars even closer to Sgr A*, searching for deviations from relativity. Any such discovery could point to new physics, perhaps uniting gravity with quantum mechanics. Sgr A* is our gateway to the universe's most profound questions. For decades, astronomers dreamed of capturing an image of a black hole's shadow. The Event Horizon Telescope, EHT, a global network of radio telescopes, made this possible. By linking observatories worldwide, the EHT achieved the resolution needed to image Sagittarius A*, the goal to see the shadow cast by the event horizon surrounded by a ring of glowing gas. In 2019, the EHT imaged the black hole in galaxy M87, but Sgr A* was a tougher target, smaller and more dynamic. Gas around Sgr A* orbits in minutes, blurring images during long exposures. The EHT team developed new algorithms to overcome this challenge. In May 2022, they unveiled the first image of Sgr A*, a bright, blurry ring encircling a dark shadow. The image matched predictions from Einstein's theory, confirming the black hole's mass and size. This achievement turned Sgr A* from theory into observable reality. Despite breakthroughs, Sagittarius A* remains full of mysteries. The EHT image is just a snapshot, raising new questions about the glowing gas's temperature, density, and magnetic fields. The black hole's spin, its speed and orientation, remains uncertain, but it shapes the surrounding space-time. Understanding Sgr A's spin will reveal clues about its formation and history. We also don't fully know how supermassive black holes like Sgr A* first formed. Did they grow from smaller black holes or collapse directly from massive gas clouds? The galactic center holds clues to these origins. EHT observations may even reveal exotic phenomena or subtle deviations from general relativity. Each new discovery brings us closer to unlocking the secrets of our galactic heart. The saga of Sagittarius A** is far from over. Occasionally, stars and gas clouds wander too close, feeding the black hole and sparking brief activity. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. This merger will funnel gas toward both galaxies' black holes, awakening Sgr A* as a brilliant quasar. Eventually, Sgr A* and Andromeda's even larger black hole will spiral together, merging in a spectacular burst of gravitational waves. The result, a new, even larger black hole at the heart of a merged galaxy, Milkomeda. This cosmic event will shape our galaxy's destiny for eons. By studying Sgr A* today, we glimpse both our past and our future. It's a reminder of our small but remarkable place in the universe's grand story. The mysteries of Sagittarius A* continue to inspire and challenge us. There are places in the universe, vast and unexplored, where gravity reigns supreme, so powerful, so absolute that nothing, not even light, the fastest thing we know, can escape. Black holes. These cosmic enigmas challenge our understanding of reality. These are not empty voids, as one might imagine, but matter crushed into an impossibly small space, a singularity of density hidden behind the event horizon, the point of no return. Most black holes are stellar remnants, a few times the mass of our Sun, formed from the collapse of massive stars. But at the centers of nearly all galaxies, lurking in the darkness, we find supermassive black holes. Monsters of gravity, millions or even billions of times more massive than our Sun. Yet even these giants, these supermassive black holes, are dwarfed by a rare and mysterious class ultramassive black holes. These behemoths, with masses tens of billions of times that of the Sun, a scale almost incomprehensible, challenge our understanding of cosmic growth and the very limits of what is possible in the universe. Ultramassive black holes are not just passive consumers of matter. They are active participants in the cosmic dance. They shape the galaxies around them, influencing their structure and evolution, regulating star formation, triggering bursts of activity, and influencing galactic evolution over billions of years. Studying them pushes the limits of our technology, requiring the most advanced telescopes and observational techniques and our theories of gravity, forcing us to confront the most extreme predictions of Einstein's theory of relativity. They are the universe's ultimate laboratories, places where the laws of physics are stretched to their breaking point, where Einstein's theories are put to the test under the most extreme conditions imaginable. How do these monsters form? What processes can create such colossal objects? What happens to the matter they consume as it spirals into the abyss? In their silent, immense presence, radiating power across unimaginable distances, we find mysteries that drive us to explore the universe's deepest secrets and push the boundaries of human knowledge. To understand ultramassive black holes, to unravel their secrets, is to glimpse the forces that have shaped the cosmos for billions of years and to understand our place within it. And at the heart of this story, at the center of countless galaxies, lies one of the most extreme examples ever found, a true cosmic titan waiting to be understood. To find an ultramassive black hole, a cosmic titan lurking in the shadows, we need to embark on a journey far beyond our immediate surroundings. We look far beyond our galactic neighborhood, past the familiar glow of our own Milky Way and its nearby companions, deep into the cosmic web, that vast, intricate network of galaxies and dark matter that spans the observable universe. Our destination, the Abell 85 galaxy cluster, a sprawling metropolis of galaxies. A city of galaxies bound by gravity, a testament to the universe's relentless pull, where countless stars swirl in a cosmic dance. Located in the constellation Cetus, a celestial whale swimming in the vast ocean of space. The light from Abell 85 has traveled 700 million years to reach us, a journey across unimaginable distances. A snapshot from a distant past, a glimpse into the universe as it existed long, long ago. At the cluster's heart sits Holm 15A, a giant among giants. The brightest and most massive galaxy in the cluster, a beacon of light and gravity dominating its surroundings. Holm 15A is a gravitational monarch, ruling over its galactic domain with an iron fist. Likely grown by cannibalizing its neighbors over billions of years, a cosmic cannibal feasting on the remnants of smaller galaxies. When we observe Holm 15A, we're witnessing the culmination of cosmic history. A story written in starlight and gravity. a place where gravity has assembled one of its grandest creations, a testament to the power of attraction on a cosmic scale. The scale is immense, dwarfing our everyday understanding of size and distance. The timescale's mind-boggling, stretching back billions of years to the dawn of the universe. But it's in these remote corners, far from the familiar, that we find the universe's most extreme phenomena, the outliers that challenge our understanding of the cosmos. Holm 15A is a beacon from the deep past, a window into a bygone era of cosmic evolution, and at its core lies a secret, a hidden giant lurking in the shadows, a black hole of truly epic proportions, an ultramassive behemoth that defies expectations. This monster challenges everything, pushing the boundaries of what's physically possible. We thought we knew about how big black holes can get, rewriting the textbooks on black hole formation and growth. Let's journey to the heart of Holm 15A and confront this cosmic enigma face to face. Nestled deep within the heart of the galaxy Holm 15A, a seemingly ordinary elliptical galaxy, lies something truly extraordinary. Lurking in its core is a black hole of such immense proportions that it defies comprehension. This is not your average supermassive black hole. This is a cosmic behemoth with a mass of 40 billion suns. It's an ultramassive black hole, a classification reserved for the most gargantuan of these gravitational titans. To truly grasp the scale of this object, imagine taking 40 billion stars, each a fiery furnace in its own right, and crushing them all together into a single, infinitely dense point. The resulting gravitational well is so profound that nothing, not even light, can escape its grasp. For comparison, consider the black hole at the heart of our own Milky Way galaxy, Sagittarius A*. It's a respectable 4 million solar masses, a significant gravitational force in its own right. But Holm 15A's black hole dwarfs it. It's a staggering 10,000 times more massive. Its event horizon, the point of no return, would be so vast that it would engulf our entire solar system, stretching far, far beyond the orbit of Pluto and into the distant reaches of the outer solar system. This black hole is not merely a component of its host galaxy. It represents a region of space larger than many planetary systems, a gravitational behemoth dominating its cosmic neighborhood. It's one of the most massive black holes ever directly measured, pushing the boundaries of our understanding. It stands as a true outlier, an anomaly in the grand tapestry of the universe. The data gleaned from Holm 15A provides invaluable insights into the upper limits of what gravity can achieve, showcasing its power on a scale rarely witnessed. This is the universe operating at its most extreme, a testament to the relentless forces of cosmic evolution playing out over billions upon billions of years. When we turn our telescopes and scientific instruments to study this black hole, we're essentially witnessing the very edge of what's physically possible within the known cosmos, exploring the boundaries of reality itself. It's a monster, a cosmic entity so immense that it almost seems to defy the laws of physics, a phenomenon that almost shouldn't exist. But the burning question remains, how did it manage to grow to such an unimaginable size? Normally, the core of a giant galaxy is packed with stars shining brilliantly, but Holm 15A's center is shockingly empty, a vast dark core spanning 30,000 light-years, almost devoid of stars. Instead of a bright, dense center, there's a hollowed-out region where our entire Milky Way could nearly fit. This emptiness defies expectations and models of galaxy formation. What could create such a desolate void in the heart of a massive galaxy? The answer points to the ultramassive black hole itself. Its formation must have involved unimaginable violence and power. The empty core is evidence of a cosmic cataclysm, a crime scene left by the black hole's growth. The stars that should be there are gone, leaving behind a ghostly silence. This discovery forces us to rethink how galaxies and their black holes evolve. The emptiness tells a story of destruction and transformation, and it all centers on the black hole's violent past. How does a black hole reach 40 billion solar masses and carve out such a void? The answer: repeated colossal mergers. Holm 15A likely formed from the collision and merger of several large galaxies, each with its own supermassive black hole. When galaxies merge, their black holes spiral together, radiating gravitational waves and eventually combining into a single, even more massive object. This process is among the most energetic in the universe, Holm 15. A's black hole didn't form in one event. It grew through a series of violent unions, each time swallowing another black hole. Each merger added mass and power, building the ultramassive black hole we see today. This is hierarchical merging, a cosmic process of growth through destruction. The giant at Holm 15A's center is a composite built from the hearts of many galaxies. It's a Frankenstein's monster of black holes, assembled over billions of years. The evidence of this brutal history is written in the empty core. But what happened to all the stars? The answer lies in the gravitational slingshot effect. As two supermassive black holes spiral together, their gravity acts like a cosmic egg beater, flinging nearby stars out of the core. Each ejected star carries away energy, tightening the black hole's orbit until they merge. Over millions of years, this process clears out the galaxy's center, creating a vast, low-density region. The more mergers, the more stars are ejected, and the larger the empty core becomes. Holm 15A's dark heart is the fossil record of this violent process. The ultramassive black hole and the empty core are two sides of the same coin. The stars aren't destroyed, they're scattered into the galaxy's halo or ejected into intergalactic space. The core's emptiness is a testament to the black hole's turbulent growth. Holm 15. A's story reveals a fundamental truth: black holes and galaxies co-evolve. Black holes aren't passive, they shape their galaxies, regulating star formation and structure. As galaxies feed their central black holes, the black holes grow, but their influence can shut down star formation by heating or expelling gas. This feedback explains why massive galaxies often stop forming new stars. The black hole acts as a cosmic thermostat, determining the galaxy's fate. Holm 15A is the most extreme example of this relationship. Its 40 billion solar mass black hole and empty core show how profoundly a black hole can dominate its environment. By studying Holm 15A, we learn how the largest structures in the universe are built and how they die. The galaxy's silent heart is a living laboratory for cosmic evolution. It's a window into the forces that shape the universe. Unraveling Holm 15. A's mystery required the most powerful telescopes on Earth. The Very Large Telescope in Chile, using the MUSE instrument, allowed astronomers to map the motions of stars in the galaxy's core. By measuring stellar speeds, they could weigh the black hole, revealing its staggering mass. MUSE also mapped the core's brightness, exposing the vast, depleted region. These observations combined to tell the story of Holm 15A's black hole and empty core. Ground-based observatories like the VLT are crucial for probing the universe's most extreme objects. They let us witness cosmic collisions and weigh the universe's greatest monsters from millions of light years away. Technology is our window into these distant, violent realms. Why does a galaxy 700 million light years away matter? Holm 15A is a signpost, testing our theories of gravity and galaxy formation at the universe's extremes. Studying such objects forces us to refine our understanding and ask new questions. The same laws that shaped Holm 15A also shaped our own Milky Way and ultimately us. By exploring the extreme, we gain insight into our own origins. To contemplate a black hole that could swallow our solar system is to be humbled by the universe's scale. This pursuit of knowledge connects us to the cosmos and drives us to keep exploring. Each discovery brings us closer to understanding the universe's grand story. Holm 15. A is not just a curiosity, it's an invitation to wonder and a reminder of the magnificent universe we inhabit. And so we continue to look up, searching for answers among the stars.